So we have a 3.5 kilogram aluminum part. So it's a metal part made of aluminum of mass 3.5 kilogram, and its initial temperature of 125 degrees C. It's plunged into a tank containing 6 kilograms of liquid water, and the water's cool at 25 degrees C. The aluminum part and the water can be modeled as incompressible with specific heat of 0.903 and the specific heat of 4.2 kilojoules per kilogram. All right, use the aluminum part and water as the system. So it's telling you that the system is both the part and the water together. Ignore heat transfer between the system and its surroundings. So from the perspective of the, it's no heat transfer. Okay, determine the final equilibrium temperature and the amount of entropy produced. I like to take two sketches. This is at time 1, this is at the final time 2. All right, so at time 1 we have our bath of cool water, and we have this hot metal part. And then later we have the bath of water with the part inside. Okay, now we have the initial temperature, well, let me not change color, temperature initial of the aluminum. Maybe you go T1 aluminum, and then the initial temperature T1 of the water. Those are given 25 and 125 degrees C. What is the final temperature of the aluminum and the final temperature of the water? Well, we don't know that, but guess what? Why are they the same? Well, they're the same because they've, after a long enough time, they've come into thermal equilibrium with each other. That's why they're the same. So the system is the combination of the aluminum part and the water together. And they come to one final equilibrium temperature. I'm going to call it T2. Okay. How do we find that temperature T2? Well, it's an energy balance. Energy balance. So you say that the total internal energy of the system is equal to the total internal energy of the system at the initial state and the final state. It didn't change. Or another way to write that is the total internal energy change is 0. Well, how do you get the total internal energy change? Well, you would bust it into two parts. You would say it's the change due to the aluminum and the change due to the water. Okay, well, how do I model the change in the aluminum? Well, how much mass is of the aluminum, the specific heat of the aluminum, and then the final temperature of the aluminum minus the temperature initial of the aluminum. Okay, and then the same thing. We have, this is for the aluminum, you have the mass times the specific heat of the water times the final temperature of the water and the initial temperature of the water. That's all equal to 0. So there's a couple steps here, but you need to get to this type of equation. Now you can solve for T2. T2 is equal to the mass times the specific heat of the aluminum times the initial temperature of the aluminum plus the mass times the specific heat of the water times the initial temperature of the water, all divided by the mass times the specific heat of the aluminum plus the mass times the specific heat of the water. It's algebra, but when you look at it, this equation makes sense. It's like a weighted average. In the weightings, the weights are based on this mass specific heat. So what I like to do is go ahead and compute what is the mass times the specific heat for the aluminum. Well, it was a 3.5 kilogram part, and the specific heat was 0.903, and so that mass times specific heat comes into 3.161. Okay, do the same thing. Mass specific heat of the water, well, it's a 6.0, and we had 4.2. The water specific heat is very high, and so when we make that multiplication, that's 25.200. This is much bigger than this one. So when you do the weighting, what you find is that T2 is equal to 3.161 times the initial temperature of the aluminum, 125, plus 25.2 times the initial temperature of the water, 25, divided by 3.161 plus 25.2, and the final temperature is a lot closer to 25 than it is to 125. It comes in at 36.14 degrees C. That's final temperature. So that's our answer for part A. All by an energy balance. Okay. Well, what about the part B? What's the amount of entropy produced within the tank? Well, you do an entropy balance. I hate to write, but anyway, it's a second law. Entropy balance. And you say that, well, how did the entropy go up? Well, just like that, the final entropy of the system minus initial entropy of the system. There's no heat transfer in or out between the system and the surroundings. And the only thing is you can have that entropy generation in the process. So sigma 1 to 2. Okay, well, how do I calculate this change in entropy? You bust it into the two mass components. So it'd be like S2 minus S1 of the aluminum plus S2 minus S1 for the water. Sigma 1 to 2. Let me just put sigma 1 to 2 on the left-hand side. And then we just have, well, how do I calculate that? Well, it's a solid, or incompressible substance. So it's the mass times the specific heat times the natural log of the final temperature divided by the initial temperature of the aluminum plus the mass times the specific heat of the water. This is all of the aluminum times the natural log of the final temperature of the water divided by the initial temperature of the water. The only thing that you have to be very careful of is, should we put Kelvin in here or can we put degrees C? We already calculated the final temperature in degrees C. Cannot put degrees C in that equation. It must be an absolute temperature scale. We must use 309.29 for the final temperature. All right, so that's one place. If a student makes an error, that's where I would look. So here it is, sigma 1 to 2. We already did the mass times the specific heat of the aluminum, 3.161. I should have put units up here. If you take a look, it's mass, which would be kilograms, times the specific heat, kilojoules per kilogram Kelvin, and the kilograms canceled. The units are kilojoule per Kelvin for both of these. All right, so kilojoules per Kelvin. Then we have the natural log of 309.29 divided by. Then we have to have the initial temperature of the water. Yeah, this one here is 298.15. I like to keep all those digits. Sometimes the textbook doesn't, but that's okay. And this one's 398.15. Good. Okay, so I don't like the way I wrote that. 0.2, what is it, 9, divided by the initial temperature of the aluminum, 398.15, okay, plus now the mass specific heat, 25.2 kilojoules per Kelvin, times the natural log, the final temperature, 305.29, divided by, and then the initial temperature of the water, 298.15. Okay, we run our calculator. Sigma 1 to 2 comes in at a whopping 0.1266 kilojoules per Kelvin. And that's our answer for part B. So energy balance, first law of thermodynamics. Entropy balance, second law of thermodynamics. For the system, which is the combination of the aluminum and the water.